Hey everyone, it's Matt. Today we're going to talk a little bit about confidence intervals for standard deviation or variance, sigma squared. To do this, we're going to need the chi-squared distribution, so that's what we're going to talk about now. This is a new Greek letter chi. It's a lot like an x. Now the chi-squared distribution has a number of uses, as you can see here in the table. We will use it primarily for confidence intervals for standard deviation and variance, as well as similar hypothesis testing, again for sigma and sigma squared. You can see a couple other ones here: goodness of fit, homogeneity, and tests of independence. We won't go through those, but these other applications exist. The chi-squared distribution, like the t-distribution, is a family of curves, so we have a number of them here. This graph here is showing a few of the curves in the chi-squared distribution. So we have chi-squared on the x-axis. The y-axis is probability density. So this is like any continuous distribution that we might be thinking about. There are a couple of different curves here depending on nu. That is our degrees of freedom. Nu is often used for degrees of freedom when thinking about chi-squared. You will notice it's not symmetric, especially for small degrees of freedom here. So this nu equal 3 is quite skewed. As nu increases, as the degrees of freedom goes up, as our sample size gets larger, it does become more symmetric. So you can see nu equals 20 here, looks a little more bell-shaped, little more symmetric. The peak here is near the mean, and we have this nice property again that when nu is larger than 30, we can approximate it with a normal distribution. So it eventually looks normal as long as our degrees of freedom is big enough. We have similar two formulas here. This is kind of like our mu x bar. In this case, the mu chi-squared is actually just equal to nu, and the variance of the chi-squared is equal to 2 nu. We won't use these particularly often, but we do have them. The function itself, for all different values of nu, does have a closed form. It does have a formula. You could write it down and you could compute these things by hand. We won't need to do that, so let's not write down the formula. Since the chi-squared distribution is not symmetric, we're actually going to have two different critical values. So this is unlike the z distribution or t distribution, where once we find z alpha over 2 or t alpha over 2, we can just take the negative of that value to give the critical value on the left. In this case, we will have two. We're going to have a chi-squared alpha over 2 and a chi-squared 1 minus alpha over 2. These two numbers will be different when we construct our confidence intervals. So let's try and compute these critical values. We have not been using Excel, but we can do so in R. So we can use the two chi-squared functions. So we can use p chi-squared and q chi-squared. These are the two functions we'll use in R. P chi-squared takes x and df, whereas q chi-squared takes probability and also degrees of freedom. So the p chi-squared is a lot like our p norm or our pt function. This value of x here gives the value of chi-squared. And we'll use this function to find the probability that chi-squared is less or equal to this input value. So this one's a lot like p norm. The q chi-squared is a lot like q norm or qt. This takes percentiles. So you can input percentiles for the chi-squared distribution, and this will give you corresponding chi-squared value. Of course, we'll also need the df, the degrees of freedom. Okay, now that we have the ability to compute these with these R functions, let's go ahead and think about constructing a confidence interval for sigma squared, the variance. There are a couple of assumptions that we need in order to be able to apply the formula that we see here. So of course, the sample must be collected using a valid random sampling technique. This is natural. The second case here is more interesting for us. It's the case that the population itself must be normally distributed, even if n is large. So in some of our other tests, if n is big enough, it doesn't really matter if the population is normal or not. But in this case, we will not be able to apply this formula in the case where our population is not normal. Let's note in particular that the chi-squared alpha over 2 that we see here, and the chi-squared 1 minus alpha over 2, these two are different. So we'll need to find each of them separately. And in particular, this means that we don't use this notation down here that we're used to using with our other statistics. It's not the case that sigma squared is well approximated by f squared plus or minus some error. The lack of symmetry of the distribution and the fact that the chi-squared alpha over 2 and chi-squared 1 minus alpha over 2 are different means that the interval won't be centered around sigma squared. So let's turn our attention now to an example. Let's imagine that we have a certain kind of wire and it has some kind of mean breaking strength. Let's say we take a random sample of 5 pieces, find their mean breaking strength as well as the standard deviation for their mean breaking strength, 5.7 pounds here. We are tasked to construct 95% confidence interval for the true standard deviation. So we have S here. We're interested in finding sigma. And as is required, we know here it is the case that breaking strength is normally distributed. This means we can use the formula on the previous page. Okay, let's get to applying this. Let's rewrite our interval formula from the previous page here. And we will need a couple of things. So we are finding 95% confidence interval. So let's have alpha be our familiar 0.05. S is known, the sample standard deviation 5.7, and our n here is 5. We don't yet have chi-squared alpha over 2 or chi-squared 1 minus alpha over 2. We'll have to find each of them. Let's draw a schematic here of the chi-squared distribution. So it's some kind of skewed distribution like this. We're interested in a particular value chi alpha over 2, as well as a particular value chi 1 minus alpha over 2. These two values will have the property that the area they section off should be 2.5%. So 0.025 probability over here, as well as 0.025 probability over here. Notice that since the distribution is skewed, to ensure that they both get 2.5%, the two values will not be the same. And so we'll compute them each separately. So let's go ahead and do that. We can do this all at once. Let's start to substitute the values that we know in our formula. So n minus 1 is 5. Let's square the standard deviation. We're going to go ahead and divide by chi squared alpha over 2. So let's use our q chi squared function. This one will be coming from 97.5% with 4 degrees of freedom. So this is a lot like qt that we're used to here. The numerator of the other will be similar. The denominator will be different. Now we will use, again, q chi squared, but this time to find x1 minus alpha over 2, we will just section off the bottom 2.5%, again with 4 degrees of freedom. So you can crunch each of these in R to find the appropriate values, and we'll simplify the numerator as well. So this comes out to about 130 over 11.1. And we can simplify the other as well. This one comes out to about 0.48. So let's finish this off here, computing both sides. So this gives us our interval for the variance sigma squared. We want standard deviation, so let's take square root of both sides to get 3.415 and 16.38. This is all in pounds, was our original problem. So now we've constructed the desired confidence interval. Notice that it is not symmetric around S. So we started with S equals 5.7. This interval is not symmetric around 5.7. Said in another way, 5.7 is not in the center of this interval. So let's notice that. This is coming because the chi-squared distribution is not symmetric. All right, that's all we've got for Unit 6. Head on over to D2L and check out the quiz.